Hi everyone. So far in the course, we've seen a lot of ways that integrals have applications in geometry, but I also want to show you an example of one of many ways that it's also used in physical sciences. For this video, I'm going to focus on the physics application of calculating work, but definite integrals really pop up in a lot of other sciences too, like chemistry and biology. I can't possibly cover every application, but it's not too difficult to find similar applications used in other disciplines with a quick internet search if you're interested in doing that. So let's give ourselves here a gentle reminder of what physicists actually mean when they use the word work. So here's the definition. Work is the amount of energy required when moving an object over a distance d by applying a constant force F. In high school science, we learned this formula that tells us work can be calculated as force multiplied by distance. So here's a really basic example you might have seen in a high school course. How much work is done by lifting a 1.5 kilogram book 2 meters off the floor? Well, this should be as easy as just applying this formula, but first we need to identify the value of the variables. We know d represents the distance the object moved, which in this case is 2 meters. But what about f? Well, whenever we lift an object, the amount of force we need to apply needs to be equivalent to the object's weight. Just be careful though. In the question, we've been given the mass of the book, but that's not the same as its weight. In high school science, we learn that we need to multiply the mass by 9.81 to get the weight. This constant, 9.81, represents the acceleration due to gravity here on Earth, and it's normally indicated by a lowercase g, as I've done here. If we were on a different planet, we would have a different gravity constant, and so the weight of the book would also be different. But here on planet Earth, 9.81 is the constant that we use. So knowing that the force can be calculated as m times g, we can rewrite our formula for work as mgd. And we know all those values, so just plug them all in to calculate the work, and that gives us a final value of 29.43. But 29.43 what? Don't forget to pay attention to the units. In this case, we can see that the units would be kilogram meters squared per second squared, but that's a really cumbersome unit to talk about. So scientists have given it a different name to this unit. This is actually what we call joules. So far, this should all be a review of what you already know from high school. So where does the integral come in? Well, there are a lot of situations when calculating work isn't so straightforward, such as when you're trying to lift fluids. Let's consider, for example, this cylindrical container, which is half full of some liquid. I've used the Greek letter rho to denote the density of this liquid, and we're going to need that later, so just hang on to that. Let's also use the letter r for the radius of our cylinder, and h will denote the height. Now I'd like to propose the following question. How much work is required to lift all the liquid out of the container? You might not immediately see why this would be any more complicated than the situation where we're lifting a book, so here is the reason. When I say calculate the work required, I'm talking about the minimum possible amount of work. And lifting the fluid out of the container would only require us to lift it to the very top of the container, as I've indicated there with that dotted line. But that means the liquid near the bottom of the container needs to travel a greater distance than the rest of the liquid. And that's unlike the book because the book is a solid, so every part of the book was traveling exactly the same distance. So we can't apply the formula F times d to calculate work because the value of d isn't clear. The distance actually changes depending on the depth of the liquid being lifted. So how can we fix that problem? This is where the integral is going to help us, and the integral implies slicing. So think about it. Imagine we were to divide the liquid into thin slices, such as the disc you see here. If that disc were thin enough, you could imagine that at least all the fluid within the disc travels approximately the same distance to get to the top of the container. The way I've depicted the disk doesn't look very thin, but as usual, what you really want to imagine in practice is an infinitesimally thin disk. This implies the following strategy. We could calculate the work done on each thin slice of liquid and call that dW, and then add up the work done on all those slices to get the total amount of work. That's where the integral is going to come in. Before we get started in working out the details, I want to remind you of an important fact about density. We just saw that calculating the work done by lifting something requires us to know the mass of the object. So we should be thinking about the relationship between density and mass, since the density is what was actually given to us here. From high school science, we know that mass is equal to density multiplied by volume. And that should make sense because, after all, density represents mass per unit of volume. With all this groundwork out of the way, let's start actually solving this problem. The first thing I like to do is set up a set of x and y axes just so that we have a scale to work with. I normally situate the x-axis at the bottom of the container, as you see here, although strictly speaking, it's not necessary to situate it there. Just be aware that if you place the axes somewhere else, your final answer might look a little bit different than mine. Now that we've set up these axes, we can use the variable y to designate the position of our sample slice, which is what we often do. And we can use dy to designate its thickness. With that, we're ready to look at the work dW, which is required for lifting each slice. That would be calculated as force times distance, so let's start with the force. We know the force required for lifting is equal to the weight of the disk, and that would be mg as discussed earlier. So now we need to know the mass of the disk, but that could be found by computing density times volume. In symbols, this means m is equal to rho times volume, but what's the volume? Well, keep in mind this refers to the volume of a disk, and we know that would be pi r squared dy, as discussed in the section on volumes. Keep in mind that this r refers to the radius of the disk, but it turns out that's the same thing as the radius of the cylinder, so I've used the same variable, capital R, to indicate that radius. So we can plug in this expression for m, and now we're done calculating the force. So next, let's look at the distance. Since the slice is being lifted to the top of the container, the distance it travels can be seen as this vertical distance. And we know that a vertical distance can be found by subtracting the y-coordinate at the top minus the y-coordinate at the bottom. Since we positioned the x-axis at the bottom of the container, we know the top will be at y equals h. And what would be the y value at the other end of the arrows? Well, that would be y equals y, the same y value that was used to position the slice itself. So subtracting these two y values gives us h minus y as the distance that our slice travels. Now that we've got our force and distance, all of this multiplies together to form dW. You'll notice I just rearranged the factors so that dy appears at the end, just because that's the notation we're used to. So we've come up with this formula for dW, which represents the work done on each slice. All that remains now is to add all these slices together to get our total work. And so our total work W is given by taking this integral. But as always, we still need to figure out the limits. Those, as always, would be the y value of our first and last slices. We know our first slice would be here at y equals 0, and our last slice would be up here at y equals h over 2. That's because our container is half full and because the x-axis was positioned at the bottom of the container. So these values of 0 and h over 2 are what we use as integration limits. Now just plug in your formula for dW and we're just about finished. Notice that rho, g, pi, and r squared are all constants being multiplied to our integral, so we're allowed to just pull them out front as I've done here. H is a constant too, but since it's not being multiplied, it can't be pulled out with these other constants. The integral can now be calculated by taking an antiderivative. And just to reiterate, we know that h is a constant, so we need to treat it as such. The antiderivative of that term would be hy, which is the same way you would antidifferentiate any other constant. And the antiderivative of y is a half y squared. Next, you would need to plug in your integration limits. So for the upper limit, anywhere we see a y, we replace it with h over 2. And similarly for our lower limit, where y gets replaced by 0, and then we subtract the results, like always when you take definite integrals. All that's left now is a bit of simple cleanup, and you'll come up with your final answer. So this formula would be used for calculating the work, and that answers the question. Of course, a cylindrical container represents a relatively easy scenario compared to, say, a conic container, which we're going to look at the next video. So look forward to that, and I'll see you next time.